An ideal cycle is shown in the figure. Its thermal efficiency is given by. So here is the cycle. Here 3 to 1 is a constant pressure process, 1 to 2 is a constant volume process, and 2 to 3 is a reversible adiabatic process. But according to second law of thermodynamics, there should be two processes. One is heat addition and another one is heat rejection to generate the work. So here we can say that 3 to 1 is a heat rejection process because at constant pressure volume is reducing, and here 1 to 2 is a heat addition process because at the constant volume pressure is rising. So that, and we can say that 2 to 3 is a working process or power output process. So here we know that thermal efficiency of a cycle is equal to 1 minus heat rejected to the heat addition or heat added. So by using this formula we can calculate the thermal efficiency of the cycle, and here heat rejected is equal to mcp T3 minus T1, and here heat addition is equal or heat supplied is equal mcv T2 minus T1. But we know that here 3 to 1 is a constant pressure process, that means V by T is equal constant, or V1 by T1 is equal V2 by T2. Sorry, here it is V1 by T1 equal V3 by T3. V by T is a constant from 3 to 1, and here constant pressure process it is, and here P by T is equal constant, that is P1 by T1 is equal to P2 by T2. So from this we can write it as T3 by T1 is equal to V3 by V1, and here T2 by T1 is equal to P2 by P1. So now take the thermal efficiency formula. Here 1 minus mcp T3 minus T1 by mcv T2 minus T1. So here mm get cancelled, and cp by cv is nothing but this gamma, that is the adiabatic index, that is 1 minus gamma into T3 minus T1 by T2 minus T1. Now take T1 as common, and here it is T3 by T1 by minus 1 by T2 by T1 minus 1. So here, but from the constant volume and from the constant pressure process, we can say that we can replace T3 by T1 and T2 by T1 by in volume and pressure terms. Here T3 by T1 can be written as V3 by V1 minus 1, and V2 by V1 can be written as P2 by P1 minus 1, and here it is 1 minus gamma into V3 minus V1 by P2 minus P1 into P1 by V1. So this is the thermal efficiency of the given cycle. So in the options, the right option is C. Consider the following statements. Availability is maximum theoretical work obtainable, and here the second one is, this is Clapeyron equation for dry saturated steam. So here it is Clapeyron equation for dry saturated steam is given by Vg minus Vf is equal to dTg by dq into Hg minus Hf by dTg. And the third statement is, a gas can have any temperature at a given pressure unlike a vapor which has a fixed temperature at a given pressure. And here the fourth statement is, Joule-Thomson coefficient is expressed as dou S by dou P at the rate of constant enthalpy. So of these statements, so here the correct statements are 1, 2 and 3, and fourth statement is wrong. Here the Joule-Thomson coefficient is dou T by dou P at the constant enthalpy. So the fourth statement is wrong, and here 1, 2 and 3 are right. 1, 2 and 3 are correct. So see here, availability is the maximum theoretical work obtainable, so that is the right, and Clapeyron equation is given by, it is also right, and a gas can have any temperature at a given pressure unlike a vapor. Consider a steam power plant that operates on the regenerative Rankine cycle with open feed water heater. The enthalpy of the steam is 3374 kJ per kg at the turbine inlet, 2797 kJ per kg at the location of bleeding, and 2347 kJ per kg at the turbine exit. The net power output of the plant is 120 megawatts, and the fraction of steam bled off the turbine for regeneration is 0.172. If the pump work is negligible, the mass flow rate of the steam at the turbine inlet is. So here the given cycle is a regenerative cycle, and let us say m is the mass flow rate of the steam at the turbine inlet. So here the fraction of steam blood of the turbine for regeneration is 0.172. That is, after the blood of some steam, the in the second stage the mass flow rate of the steam is 1 minus 0.172 into m. So that here for the first stage here mass flow rate is m, and for the second stage the mass flow rate is 1 minus 0.172 into m. And in the first stage the enthalpy drop from the 3374 to 2797, that is at the location of bleeding. This is the first enthalpy drop in the first stage, and in the second stage the enthalpy drop is from 2797 to 2347 kilojoule per kg. So that the total power developed by the turbine is equal to, let us say P is equal m into 3374 minus 2797 minus plus 1 minus 0.172 into m into 2797 minus 2347. So which is equal to the power output of the turbine is given as 120 megawatts. So here m into 950 is equal to 120 megawatts, that is 120 into 10 power of cube kilowatts. So m is equal to 120 into 10 cube by 950, which gives a value of nearly 126 kg per second. So in the option, the right option is B. For a cup shown in figure, the length of wire required is. So here is a given diagram, 50 cm of diameter and 60 cm of height. So for this case, the length of wire required is equal to d square plus 4dh, where d is the diameter of the cup and h is the height of the cup. Here d is 50 square plus 4 into 60 into 50. So it gives a value of 120.4 centimeters. In an orthogonal cutting test on mild steel, the following data were obtained. So here the data is cutting speed is equal to 40 meter per minute, depth of cut is equal to 0.3 mm, tool rake angle is equal to 5 degrees, chip thickness is equal to 1.5 mm, cutting force is equal to 900 Newton, thrust force is equal to 450 Newton. Using Merchant's analysis, the friction angle during machining will be. Here, by using Merchant's analysis, coefficient of friction is given by Fc sin alpha plus Ft cos alpha by Fc cos alpha minus Ft sin alpha, where Fc is the cutting force and Ft is the thrust force, and here alpha is the rake angle. So here all the values are given. So Fc is 900 Newton and Ft is 450 Newton and alpha equal 5 degrees. Substitute all these values and we can get here mu is equal to 0.614, and the friction angle is given by tan inverse of mu, where mu is the coefficient of friction. So here tan inverse 0.614, which gives a value of 31.5 degrees. So in the option, the right option is B. B is the right answer.